So in this video, we're going to continue on with our look at partial fraction decomposition. And it turns out that for partial fraction decomposition, we can always write out our polynomial, or a rational function, which is a polynomial over a polynomial. We can always write that out as sums of things that look like this, or this. All right, for some k here. All right, and this is actually what this breaks up into. So if we have the denominator has a certain form, then in our partial fraction decomposition, we will get the form that I put over in this side of the table. Okay, so one thing we could have in the denominator, if in the denominator we have ax plus b, so some linear term, then the fraction that we get over on the right side when we try to decompose will look like a constant over ax plus b, all to the first power in the denominator there. So k is 1 here. If we get ax plus b raised to the k in the denominator, then the fraction form over on the far right will look like some constant over ax plus b plus some other constant over ax plus b squared. And we do that until we get to ax plus b to the kth power. And it turns out that we'll be able to write our fraction over this, something like this, so some polynomial over something like this, that'll decompose into a sum that looks like this over here on the right. Okay. Well, we can also have quadratics in the denominator. So if we get something like ax squared plus bx plus c, then we could have something like ax plus b, so it'll be a linear term up in the numerator over ax squared plus bx plus c. And just like before, it turns out if we have some power on this quadratic here, then it really turns into a sum of things like a1x plus b1 all over ax squared plus bx plus c, and we add that up until we get to some a sub k x plus b sub k all over ax squared plus bx plus c to the kth power. Okay, cool. So it turns out that we will always be able to write our rational function or polynomial over a polynomial as a sum using this pattern or this idea here. So let's go ahead and write out some examples to see what that looks like. So, for example, let's write out the form of the partial fraction decomposition given a certain function here. So let's suppose we were trying to solve the integral x to the 7th plus 8x to the 5th plus 3 all over x plus 1 times x minus 3 cubed, all times x squared plus x plus 1 squared dx. And this denominator is already in factored form here. And what is its power? Well, we got an x squared and then squared. So this factor right here is an x to the 4th. This is an x cubed, so we get x to the 4th times x cubed is x to the 7th, times another linear term over here, so we have an x to the 8th, a degree 8 polynomial in the denominator. In the numerator is a degree 7 polynomial, so the degree of the denominator is higher than the degree of the numerator, so we do not need to do polynomial long division first. We can immediately write this in the form that we want, and let's just write out what that form is. And so this fraction, x to the 7th plus 8x to the 5th plus 3 all over x plus 1 times x minus 3 cubed times x squared plus x plus 1 to the 2nd power. All of that is going to be equal to, and now let's write out what this is term by term. So we have a factor of a linear term in the denominator. If we look at above, that says that we have something like a over that linear term. And the power on that was 1, so we're done with that. But then we have another factor here, x minus 3, and that cubed. So we're going to get some b, and I'm going to say b1 here, over x minus 3, plus some b2 over x minus 3 squared, plus b3 over x minus 3 cubed. And again, we go and we keep doing this. We keep writing something out like this until we get to the power on that linear term. Okay? And of course, we're not quite done yet because we have a quadratic term there. If we have a quadratic in the denominator, though, an irreducible quadratic, right? This doesn't factor anymore. Then we have to have a linear term up in the numerator. So this is going to be some c, and I'm going to go ahead and say 1 here, c1x plus d1 all over x squared plus x plus 1. And then we're going to have plus some c2x plus d2 all over x squared plus x plus 1 squared. Now, we're not going through why this is the case, but it turns out always this right here over on the left, this polynomial, or sorry, a rational function, polynomial over polynomial, can be separated into the sum of these kinds of fractions. So here is the form of our partial fraction decomposition. Now, this algebra here to solve for a, b1, b2, b3, c1, d1, c2, d2, the algebra here would be quite intensive. So we're not going to do that on this problem. We just wanted to write out what the form would look like over here. But we could do the algebra to solve for these. And once we did that, we could finish out the integral because this is a natural log. This is a natural log when we do the integral. This is going to be a u sub with u equal to x minus 3. And so we're going to get something like u to the negative 2, which we can integrate, and u to the negative 3, which we can integrate. And then we've seen stuff like this. Here we can factor it into cx over x squared plus x plus 1. And then we will be able to deal with that. We might have to manipulate the denominator a little bit, but we would be able to turn this into a perfect square. And then we can have a u sub with the cx part, and then a constant over that thing with the perfect square, at least a x squared minus a perfect square. We could turn into an arc 10 problem, which we've done in the past. And so we could do stuff like that for these terms over here. All right. But for now, we're actually just going to pause this video here, and then we'll do a couple of full examples of these types of problems now that we know how these things break up into their partial fraction decomposition.